Okay, so hello everyone. And first, we want to explain that there is descriptive statistic where we organize raw data into a frequency distribution and compute several measures of location and measures of dispersion to describe the major characteristic of the distribution. And then second, there is probability, and from probability statements, we can create probability distribution. And then the third is statistical inference, where we collect a sample to estimate a population parameters such as the population mean or population proportion. In addition, we use the sample data to test an inference or hypothesis about a population mean or a population proportion, the difference between two population means, or the equality of several population means. So each of these tests involve just one interval or ratio level variable, such as profit made on car sale, the income of bank presidents, or the number of patients admitted each month to a particular hospital. So in this video, we will study the relationships between two interval or ratio level variables. In all businesses field, identifying and studying relationships between variables can provide information on ways to increase profits, methods to decrease costs, or variables to predict demand, such as in marketing products. Many firms use price reduction through coupons and discount pricing to increase sales. In this example, we are interested in the relationship between two variables, such as price reduction and sales. And to collect the data, a company can test market a variety of price reduction methods and observe sales. We hope to confirm a relationship between that decreasing price leads to increased sales. Like in economics, you will find many relationships between two variables that are the basis of economics, such as supply and demand and price, and etc. On to the question. Question number one. Find a relationship between two variables on the basis of economics. So, in this material, we carry this idea further, that is, developing numerical measures to express the relationship between two variables. Is the relationship strong or weak? Is it direct or inverse? In addition, there is an equation to express the relationship between variables, and this will allow us to estimate one variable on the basis of another. So to begin our study of relationship between two variables, we examine the meaning and purpose of correlation analysis. We continue by developing an equation that will allow us to estimate the value of one variable based on the value of another. This is called regression analysis. We will also evaluate the ability of the equation to accurately make estimation. So, what is correlation analysis? Studying the relationship between two interval or ratio scale variables. First, we start with a scatter diagram. This procedure provides a visual representation of the relationship between the variables. And then second, we calculate the correlation coefficient. It provides a quantitative measure of the strength of the relationship between two variables. For example, the sales manager of Copier Sales of America, which has a large sales force throughout the United States and Canada. They want to determine whether there is a relationship between the number of sales calls made in a month and the number of copiers sold in that month. The manager selects a random sample of 10 representatives and determines the number of sales calls each representative made. So here is the table of sales calls and copiers sold for 10 salespeople. By reviewing this data, we observe that there does seem to be some relationship between the number of sales calls and the number of units sold. That is, the salespeople who make the most sales calls sold the most units. However, this relationship is not perfect or exact. For example, Sonny Jones made fewer calls than Jeff Hall, but she does sell sold more units. So from this data, we will develop numerical measures to precisely describe the relationship between the two variables, sales calls and copiers sold. This group of statistical techniques is called correlation analysis. So correlation analysis is a group of techniques to measure the relationship between two variables. Now we on to the question number 2. Please give an example of the imperfect relationship between two variables. And now we move on to the correlation coefficient. Correlation coefficient was originated by Carl Pearson about in 1900. The correlation coefficient describes the strength of the relationship between two sets of interval scaled or ratio scaled variables. Or we can say a measure of the strength of the linear relationship between two variables. Designated R, it is often referred to as Pearson R and as the Pearson product moment correlation coefficient. And the next is characteristic of the correlation coefficient. So first, the sample correlation coefficient is identified by the lowercase of letter r. And then second, it shows the direction and strength of the linear relationship between two interval or ratio scale variables. The third is it range up from -1 up to including +1. And the fourth is a value near zero indicates there is little relationship between the variables. The fifth is a value near 1 indicates a direct or positive relationship between the variables. And the ninth and the sixth is a value near -1 indicates inverse or negative relationship between the variables. And the last is a correlation coefficient -1 or +1 indicates perfect correlation. The strength of the correlation does not depend on the direction, either minus or plus. So coefficient of -0.91 and plus 0.91 have equal strength. They both indicate very strong correlation between the two variables. So while we study about correlation coefficient, we also should know what is scatter diagram. A scatter diagram, also known as scatter plot or scatter graph and scatter correlation chart, is a tool for analyzing relationship between two variables for determining how close the two variables are related. If the variables are correlated, the points will fall along a line or curve. The better the correlation, the tighter the points will hug the line. Or we can say that if the correlation is weak, there is considerable scatter about a line drawn through the center of the data. For the scatter diagram representing a strong relationship, there is very little scatter about the line. And the next is how to make scatter diagram. To make scatter diagram, first draw a vertical line through the data value at the mean of the x values, and a horizontal line at the mean of y values. These lines pass through the center of the data and divide the scatter diagram into four quadrants. Two variables are positively related when the number of y is above the mean and the number of x is also above the mean. These points appear in the upper right quadrant, labeled quadrant 1. Similarly, when the number of y is less than the mean, so is the number of x. These points fall in the lower left quadrant, labeled quadrant 3. If the two variables are inversely related, one variable will be above the mean and the other below the mean. Most of the points in this case occur in the upper left or and lower right quadrants, that is quadrant 2 and quadrant 4. But what will happen if there is no linear relationship between the two variables? The points in the scatter diagram will appear in all four quadrants. Now, maybe you guys curious, how is the value of correlation coefficient determined? How do we know the value is 0 or 1 or maybe -1? Okay, so to determine the value of the correlation coefficient, we use this kind of formula that's shown below. And we will use the copier sales of America data as an example. The sum of the products of deviations from the representative means is 900. To compute the correlation coefficient, we use the standard deviation of the sample of 10 calls and 10 copiers sold. The standard deviation of the number of sales calls is 9.189, and the number of copiers sold is 14.337. Using the standard deviation formula, we now insert these values into the correlation coefficient formula, and then we get 0.759. Now, how do we interpret a correlation of 0.759? First, it is positive, so we conclude that there is a direct relationship between the number of sales calls and the number of copiers sold. The value of 0.759 is fairly close to 1, so we conclude that the association is strong. Now we on to the question. Is it true that if there is a strong relationship between two variables, let's say it's 0.759, always mean that an increase or decrease in one variable causes a change in other variable? Please explain your answer. The answer is no. If there is a strong relationship between two variables, we are tempted to assume that an increase or decrease in one variable causes a change in the other variable. But it's not necessarily true. We have not demonstrated cause and effect here, only that the two variables are related. For example, it can be shown that the consumption of Georgia peanuts and the consumption of aspirin have a strong correlation. However, this does not indicate that an increase in the consumption of peanut causes the consumption of aspirin to increase. Relationships such as this are called spurious correlation. What we can conclude when we find two variables with a strong correlation is that there is a relationship or association between the two variables, not that a change in one causes a change in the other. Okay, now let's continue to the scattered diagram example. Draw a vertical line through the data values at the mean of the x values, and a horizontal line at the mean of y values. So, based on that data, in previous example, we've added a vertical line at 22.0 calls and a horizontal line at 45 copiers sold. And this is the scattered diagram of the example we use. For example, the last person on the list, Sonny Jones, made 30 sales calls and sold 70 copiers. These values are above their respective means. So, this point is located in quadrant 1, which is in the upper right quadrant. She made more 8 sales calls than the mean and sold 25 more copiers than the mean. That's it for correlation coefficient. Now we move on to the next topic, that is testing the significance of the correlation coefficient. The correlation coefficient R tell us about the strength of the linear relationship between x and y. However, the reliability of the linear model also depends on how many observed data points are in the sample. For example, the correlation between the number of sales calls and the number of copiers sold was 0.759. So this indicates a strong positive association between the two variables. However, only 10 salespeople were sampled. Could it be that the correlation in the population is actually zero? This would mean the correlation of 0.759 was due to change. If we had data for the entire population, we could find the population correlation coefficient. But because we only have sample data, we cannot calculate the population correlation coefficient. The sample correlation coefficient, or R, is our estimated of the unknown population correlation coefficient. We now perform a hypothesis test of the significance of the correlation coefficient to decide whether the linear relationship in the sample data is strong enough to use the model the relationship in the population. For example, we will continue with the illustration involving sales calls and copier sold. We employ the 5 hypothesis testing steps, that is, step 1, state null and alternate hypothesis. And then step 2, select a level of significance. Step 3, identify the test statistic. Step 4, formulate a decision rule. And then step 5, take a sample, arrive at the decision. The null hypothesis and the alternate hypothesis are like this. The correlation in the population is zero, and then the correlation in the population is different from zero. From the way it's stated, we know that the test is two-tailed. So the formula for T is shown right here. Using the 0.05 level of significance, the decision rule in this instance state that if the computed falls in the area between plus 2.306 and minus 2.306, the null hypothesis is not rejected. So how do we get the number of 2.306? 306. Okay, let me explain. Because the test is two-tailed and we use the 0.05 level of significance, and the F equals to 9 minus 2 equals to 10 minus 2 equals to 8. So based on this students distribution table, we get 2.0306. Applying the formula to the example regarding the number of sales calls and units sold, we get 3.297. The computed T is in the rejection region. Thus, H0 is rejected at the 0.05 significance level. Hence, we conclude the correlation in the population is not zero from a practical standpoint. It indicates to the sales manager that there is correlation with respect to the number of sales calls made and the number of copiers sold in the population of salespeople. Now on to the question, how do you know if a correlation coefficient R is significant?
Now we moved on to the regression analysis. Regression analysis is a technique that helps us to analyze relationships between variables to better understand the world around us. Variables are items of data that describe an attribute or characteristic of an object or participant. They can be categorical placing objects or participants into discrete groups, or continuous placing an object or participant somewhere on a scale according to a specific attribute. In data analysis, variables can be assigned as predictors, also known as independent variables, or outcomes, or also called dependent variables. There are many applications for regression analysis. Within longitudinal studies, we can examine how early life circumstances or characteristics relate to outcomes in adulthood, middle age, or later life. For example, we may want to see whether there is a clear relationship between people's academic performance at school and their life satisfaction in middle age. On to the question, why is regression analysis very important in statistical calculations? Okay, time is up. Now we want to develop a linear equation that expresses the relationship between the number of sales calls and the independent variable and the dependent variable. The equation for the line used to estimate y on the basis of x is referred to as the regression equation. So regression equation is an equation that expresses the linear relationship between two variables. And now, using scatter diagram, we can plot the life satisfaction score of individuals in our sample against their average academic achievement. We can see that there is a pattern, but can we say how much more satisfied with life people can expect to be if they average 1 grade point higher in school? How about if they average half a grade point lower? We can summarize the data on the graph by drawing a line roughly to the middle of all the data points, as you guys can see here, the graph. And this is the regression line, and we can use it to estimate or model the relationship between our independent and dependent variables. From this model, we can predict that someone who had a grade point average of 2.5 will approximate life satisfaction score of 7.6 out of 10. So you can see in the graph. And the next graph, this is around 0.8 lower on average than someone with a GPA of 3.5, whose life satisfaction score will be around 8.4. So it is important to remember that the line is just an estimation and will not predict the outcome perfectly. And one of the advantages of regression analysis is that this simple model can be extended to include more and more independent variables. This is important as it allows us to adjust for variables such as confounders. And on to the question, what is the example of a regression analysis that can help you in your daily life? Time is up. Now we move to the testing the significance of this slope. The next step is to analyze the regression equation by conducting a test of hypothesis to see if the slope of the regression line is different from zero. Why is this important? If we can show that the slope of the line in the population is different from zero, then we can conclude that using the regression equation adds to our ability to predict or forecast the dependent variable based on the independent variable. If we cannot demonstrate that this slope is different from zero, then we can conclude that there is no merit using the independent variable as a predictor. To put it another way, if we cannot show the slope of the line is different from zero, we might as well use the mean of the dependent variable as a predictor rather than use the regression equation. So following from the hypothesis testing, the null and alternative hypotheses are if H0 is equals to zero and not equals the H1 not equals to zero. We use beta, the Greek letter beta, to represent the population slope for the regression equation. This is consistent with our policy to identify population parameters by Greek letters. We identified the slope value as B. So our computed slope B is based on a sample and is an estimate of the population slope, identified as beta. The null hypothesis is that the slope of the regression equation in the population is zero. If this is the case, the regression line is horizontal and there is no relationship between the independent variable x and the dependent variable y. So in other words, the value of the dependent variable is the same for any value of the independent variable and does not offer us any help in estimating the value of the dependent variable. And what if the null hypothesis is rejected? If the null hypothesis is rejected and the alternate hypothesis accepted, this indicates that the slope of the regression line for the population is not equal to zero. That is, knowing that the value of the independent variable allows us to make a better estimate of the dependent variable. To put it another way, a significant relationship exists between the two variables. To test the null hypothesis, we use the t distribution with the n-2 and this is the following formula, where b is the estimate of the regression line's slope calculated from the sample information. SB is the standard error of the slope estimate, also determined from sample information. Our first step is to set the null and the alternative hypothesis. So H0 beta is greater or than zero, less or equals to zero, and H1 is beta is greater than zero. Notice that we have one tailed test. If we do not reject the null hypothesis, we conclude that that the slope of the regression line in the population could be 0. So this means the independent variable is no value in improving our estimate of the dependent variable. If we reject the null hypothesis and accept the alternative, we conclude the slope of the line is greater than 0. Hence, the independent variable is an aid in predicting the dependent variable. Question: what are the steps to conduct a hypothesis test for a regression slope? Time is up. And next is the evaluating a regression equation's ability to predict. So the standard error of estimate is the measure of a variation of an observation made around the computed regression line. So simply, it is used to check the accuracy of predictions made with the regression line. It is the estimation of the accuracy of any predictions. In other words, the standard error of estimate is used to determine how well a straight line can describe values of a data set. When you have a collection of data from some measurement, experiment, survey, or other source, you can create a line of regression to estimate additional data. With the standard error of estimate, you get a score that describes how good the regression line is. It is denoted as SAE. SAE is the square root of the average squared deviation. It is the same concept as the standard deviation, but standard deviation measures the dispersion around the mean, and the standard error of estimate measures the dispersion about the regression line. The deviation of some estimates from intended value is given by standard error of estimate formula. So here, as you guys can see, the numerator is the sum of the squared differences between the actual value of each observation and it is predicted value. It's the sum of the squared error terms. The denominator is the number of observations minus 2. Just like when calculating a sample standard deviation, but it is to divide it n minus 1. And for this, we are dividing by n minus 2. That's because we are estimating 2 parameters. So to calculate the degrees of freedom, you need to subtract 2. That will make the estimate unbiased. So here, x is the actual score, and the x bar is the predicted score, and the n is the total number of observations. For a regression model that has a small standard error of the estimate, the data points will be closely packed around the estimate regression line. As you guys can see here, the data points are closely packed around the estimated regression line. And conversely, for a regression model that has a large standard error of estimate, the data points will be loosely scattered around the regression line. And for an example of the standard error of estimate, here there's data. We get the data that n equals to 5, and the square error, which is SS error, is 14.4. So we put it in the formula, SEE equals to root 14.4 divided by 5 minus 2, which is 3, and we got the result equals to 2.19. So the standard error of estimate, we got 2.19. Next is the coefficient of determination, defined as the proportion of the total variation in the dependent variable y that is explained or accounted for by the variation in independent variable x. The coefficient of determination, or R2, is used to analyze how differences in one variable can be explained by a difference in a second variable. More specifically, R squared gives you the percentage variation in y explained by x variables. And the range is from 0 to 1, or example 0% to 100% of the variation in y can be explained by the x variables. The coefficient of determination is similar to the correlation coefficient, R. The correlation coefficient formula will tell you how strong of a linear relationship there is between the two variables. R squared is the square of the correlation coefficient. The coefficient of determination can be thought as a percent. It gives you an idea of how many data points will fall within the results of the line formed by the regression equation. The higher the coefficient, or the higher percentage of points the line passes through when the data points and line are plotted. If the coefficient is 0.80, then 80% of the points should fall within the regression line. Values of 1 or 0 will indicate the regression line represents all or none of the data, respectively. A higher coefficient is an indicator of a better goodness of fit for the observations. The coefficient of determination can be negative, although this usually means that your model is a poor fit for your data. It can also become negative if you didn't see an intercept. So clearly, this data does not form a perfect line. Instead, the data are scattered around the best fitting least square regression line, and there will be error in the predictions. So here is the relationships among the correlation coefficient, the coefficient of determination, and the standard error of estimate. Recall that it measures how close the actual values are to the regression line. When the standard error is small, it indicates that the two variables are closely related. In the calculation of the standard error, if the value of this term is small, then the standard error will also be small. The correlation coefficient measures the strength of the linear association between two variables. When the points on the scatter diagram appear close to the line, we note that the correlation coefficient tends to be large. Therefore, the correlation coefficient and the standard error of the estimate are inversely related. As the strength of a linear relationship between two variables increases, here is the relationship among the correlation coefficient, coefficient of determination, and the standard error of estimate. And a convenient vehicle for showing the relationship among these three measures is an ANOVA table. As you guys can see here, the yellow highlighted portion of the spreadsheet ANOVA table. The total variation is divided into two components. One is the variation explained by the regression, explained by the independent variable, and two is the error or residual. This is an unexplained variation. These three categories are identified in the first column of the spreadsheet ANOVA table. So the column headed DF refers to the degrees of freedom associated with each category. The total number of degrees of freedom is n-1. The number of degrees of freedom in the regression is 1 because there is only one independent variable. The number of degrees of freedom associated with the error terms is n-2. The term as located in the middle of the ANOVA table refers to the sum of squares. You should note that the total degrees of freedom is equal to the sum of the regression and residual or error degrees of freedom. And the total sum of squares is equal to the sum of the regression and residual sum of squares. This is true for any ANOVA table. And the ANOVA sum of squares are computed as follows. Regression sum of square equals SSR equals to 1065.789. And residual error of sum of squares SSE equals to 784.211. And the total sum of square SS total equals to 1850.00. Recall that the coefficient of determination is defined as the percentage of the total variation, explained by the regression equation, SSR. Using the ANOVA table, the reported value of R squared can be validated. As you guys can see, using the values of ANOVA table here, the coefficient of determination is 1065.789 divided with 1850.00, and it is equals to 0 0.576. Therefore, the more variation of the dependent variable explained by the independent variable, the higher the coefficient of determination. The final observation that relates the correlation of coefficient of determination, and the standard error of estimate is to show the relationship between the standard error of the estimate and SSE by substituting into the formula for the standard error of estimate. So in sum, regression analysis provides two statistics to evaluate the predictive ability of a regression equation: the standard error of the estimate and the coefficient of determination. And when reporting the result of a regression analysis, the findings must be clearly explained, especially when using the results to make predictions of the dependent variable. The report must always include a statement regarding to the coefficient of determination so that relative precision of the prediction is known to the reader of the report. On to the question, what will happen if the standard error of estimate is large? So what will happen if the standard error of estimate is large? Time is up. Now we moved on to the interval estimates of prediction. The standard error of the estimate and the coefficient of determination are two statistics that provide an overall evaluation of the ability of a regression equation to predict an dependent variable. And another way to report the ability of a regression equation is to predict the specific to a state value of the independent variable. And before we present the confidence intervals, The assumptions for properly applying linear regression should be reviewed. Now, the first is for each value of x, there are corresponding y values. These y values follow the normal distribution. Second, the means of these normal distributions lie on the regression line. The standard deviations of these normal distributions are all the same. The best estimate we have of this common standard deviation is the standard error of estimate. Fourth, the y values are statistically independent. This means that in selecting a sample, particular x does not depend on any other value of x. This assumption is particularly important when data are collected over a period of time. Such a situation, the errors for a particular time period are often correlated with those of other time periods. Now is the constructing confidence and prediction interval. So when using a regression equation, two different predictions can be made for a selected value of the independent variable. The differences are subtle but very important and are related to the assumption stated in the last section. Recall that for any selected value of the independent variable x, and the dependent variable y is a random variable that is normally distributed with a mean y. Each distribution of y has a standard deviation equal to the regression analysis standard error of the estimate. And now the first interval estimate is called confidence interval. This is used when the regression equation is used to predict the mean value of y for a given value of x. For example, we would use a confidence interval to estimate the mean salary of all executives in the retail industry based on their years of experience. And to determine the confidence interval for the mean value of y for a given x, the formula is this, as you guys can see. And the second interval estimate is called a prediction interval. This is used when the regression equation is used to predict an individual y n equals to 1 for a given value of x. And for example, we would estimate the salary of a particular retail executive who has 20 years of experience. And to determine the prediction interval for an estimate of an individual for a given x, the formula is this. On to the question, when do we use confidence interval and prediction interval? So that's all, guys, for our presentation. And thank you so much for listening. See you on the other video. Bye.